Lesson 10.6, Exponential Growth and Decay. Now we're going to get specific in terms of what kind of growth is occurring with respect to exponential growth. When we talk about rate of decay or growth, we have basically two types of questions. One is if it's more calculating, meaning is your rate of growth or decay calculated annually or biannually, monthly, and so on, or is it naturally? And of course, nature never rests. So if nature never rests, it is compounded continuously. So it's decaying constantly or growing constantly. And when you approach it that way, you're looking at a different type of equation. So we have two equations, and that's the difference. Here is these two right here are growth and decay with a calculated approach. When you have these two, you're talking about a constant rate of growth or decay. And that's, again, more preferred by scientists because that is indeed what nature is all about in science. More calculating in terms of changing constantly. No rest. One little note here, if you're dealing with carbon-14, your K value is 0.00012, and we'll talk about that in a moment. So here's a question. We have a cup of coffee that contains 130 milligrams caffeine. Caffeine is eliminated from the body at a rate of 11% per hour, and per hour is big. How long will it take for 90% of the caffeine to be eliminated? Now, one important part here to understand, if you are eliminating 90%, then let's understand that that means that there is 10% left in the body. Very important to understand that. Now, since they say 11% per hour, we're going about this in a more calculating manner. So we're going to choose the rate of decay that is not involving E. So here we have A, which is our initial amount, and 1 minus R, which is our rate. So I'm going to put in the rate. So 11% is our rate, and T. A is 130, and we're wondering when there's 10% of that left. So if we calculate 10% times 130, we will get 13. I'll put 13 over here. That's what we want. We want to see how long it takes to get 13 left. 13 milligrams of caffeine. Divide both sides by 130, and something interesting happens. Now I'm going to change 1 minus 0.11 to 0.89. 13 divided by 130, well, that's 0.1. So if you notice, we really didn't even have to put in the 130 initial amount and to calculate the 13, what's left, because they're wondering about having 10% left, and that is basically over here. So you'll notice this in the next couple of questions as well. Well, in this situation, we can't get to the variable because it's in the exponent, so we rely on our log. And you can do log or natural log. It does not matter. You're going to get the same answer. So I would do that to both, and I would get ln.1 equals t ln.89. I would divide both sides by ln.89, and t would be 19.8. In other words, t would be approximately 20 hours. It would take that long for you to eliminate 90% of the caffeine in your body. Next question. A half-life of sodium is 2.6 years. What's K? So if we take a look at that, now this is half-life, so it sounds calculating, but half-life is referring to natural decay of an element. So let's use E. That would give us A e to the negative k t, and they want us to find k. All right, well, again, we're talking about having half as much left. So if I go 0.5, half of A, when you start with A. Now, we don't know K, but we do know T. It's 2.6 years. Now, if I divide both sides by A, again notice that I end up basically just canceling out the A's, and I end up with my amount left as before. But now I have E to the negative K 2.6, and I should write 2.6K there. But now if we ln both sides, this one works really well with ln because it's E, and we get ln 0.5 equals, and these cancel, and you get negative 2.6K. Divide both sides by negative 2.6, and K will be ln 0.5 divided by negative 2.6. So K is equal to 0.2666 if we go to 4 decimal places. Now we're talking about carbon-14, and for food for thought here, I had it before, but carbon-14, the K value is equal to 0.00012. We realize that there's only 3% left. How long ago did the mammoth die? So we're talking about natural decay, so again we're going to use y equals a e to the negative k t. We actually know k this time, so it's going to be negative 0.00012 t. Now there's 3% left. Now I could write 0.3a over here, or 0.03a, but again we know the a's will cancel, so I'm going to go right to this point. 0.03 equals e to the negative 0.00012 t. Let's do ln again, and we get ln 0.03 equals, and these cancel, negative 0.00012 t. Divide both sides by negative 0.00012, and t will give you ln 0.03 divided by negative 0.00012, which is about 29,221 years. Population growth. You have a rate of growth, and it's per year. So we're going to do growth with respect to more calculating. So y equals a 1 plus r to the t. Now again, I could put a million right here, and then write 2 million over here. But when I divide both sides, I'm going to end up with 0.5. Or excuse me, I'm going to end up with 2, because it's doubling. And it's 0.03 to the t. So again, 2 equals 1.03 to the t power. Now again, you can use log or natural log. I just get used to using natural log here. Again, it does not matter. ln 2 equals t, because I'm going to bring the power down, and have ln 1.03. Divide both sides by ln of 1.03, and t will equal ln 2 divided by ln of 1.03, which will give you about 24 years. Now our last piece here, real quick, I have about a minute, is to show an equation that's modified for money. We have the P for initial amount, or A before. Your R is your rate of growth, okay, and T is your time. And you would put 1,000 in there. You have 5% interest. There's your interest time, and then 10 years, you get this amount. So this is more applied for money. The same idea. In this one, very important to look at least means the amount that you have is greater than or equal to 1,500. You get to this situation, you divide by 1,000, and then you do ln both sides, and these cancel, and you divide both sides by 0.05 and get your answer. And this ends lesson 10.6.